Oh, do I have any chalk? Good chalk. Okay. All right. Oh, everybody's here. Okay. What I'm hoping is that after what I've covered today, you'll have seen enough to work on the very first homework problem, which is the only one that doesn't require MATLAB. So first, a very quick section, which is so quick it's almost seems pointless, but actually, for concepts, we just don't take very long to talk about. Okay, so there are two types of solutions to a PDE, classical or weak. And so first I'll give the formal definition, and then I'll translate it into English. So first, some notation. So this notation, CK, is not C to the kth power. That's one of the difficulties with getting into this level of math, is that superscripts are used all the time and very often not meant to be exponents. So you have to avoid making an assumption. So CK is the space of functions that have at least k continuous derivatives. Okay. And now, often this space is indicated with some sort of domain, like an interval or something like that. Here I haven't given one, which means functions of these k continuous derivatives on the entire space, like the whole real number line, or Rn for whatever n might be. And then in regard to, so this is called a function space, which is a kind of vector space. Now, when I say vector, you typically think of vectors in R2 or R3, the points in space. But really, vectors are any kind of entity that you can add them and you can multiply by a number. And we certainly know how to do both of those things with functions. So we have spaces whose vectors are functions. So that's when I say a space of functions, that's what I mean. I guess I didn't really need this, because then I'm saying function space of functions. Okay. Now, so in this context, C is just with no superscript. It's just a space of continuous functions without comment on their derivatives. So for example, the absolute value function is in C, it's continuous, but it is not in C1. So because it does not have a continuous derivative. Its graph has this kink at x equals 0. So it fails to have a continuous first derivative. Okay. All right. So, we're supposed to have a function u as a solution of a kth order PDE. So in other words, the highest order derivative anywhere in the PDE is order k. So how do we know if this solution is classical or weak? So in terms of function spaces, it's very easy to say. If it's classical, if its kth order derivatives actually exist and are continuous. And then weak otherwise. Okay. Okay. So another way of putting it is a classical solution is one that you can actually substitute into the PDE and actually compute all the derivatives that the PDE has in it. So you're able to actually plug and chug it in, and not have any case of something being undefined. So for instance, I could not if this was a solution to a PDE, even of first order, it could never be a classical solution because it doesn't even have one continuous derivative. But it could possibly be a weak solution. So weak solutions are solutions that have some discontinuity somewhere, like maybe the solution itself is discontinuous, or maybe one of its derivatives is discontinuous. All right. So a couple examples involving weak solutions, which actually tend to come up fairly often in applications. So this PDE So this is a second order PDE because I have b of x u prime, and then I take a derivative of all of that. And when I take a derivative as product rule would produce a u xx. Yes. So that's some coefficient. Here are boundary conditions. You had a lot of fun with those last time. And then I'll define B. B is a piecewise constant coefficient. Something you, Sarah, would especially know something about. Okay, so we're on the interval 0 to 1. So it's equal to 1 for x less than a half and 2 otherwise. Okay. So you can think of this as if I were to apply this definition let's see. So it's almost like I'm saying if the equation, the PDE is u double prime is equal to 0 on this half, and then 2u double prime is equal to 0 on the other half, but then we also have these boundary conditions to satisfy. So here's a solution. So now, if a PDE is equal to u double prime equals 0 on the first half, and then 2u double prime equals 0 on the second half, anytime u double prime equals 0, if the function's second derivative is 0, that means it's a linear function. So we know that much. So in fact, this function that is linear on each piece. So it's 4/3 x, and x is less than a half, and 2/3 x plus 1/3 when x is greater than or equal to half. So if I plug in x equal to 1/2 in both of these formulas, I'm going to get 2/3 for this one, and then I'll get 1/3 plus 1/3 is also 2/3. So these coefficients are chosen to make sure that the two pieces join up.
So you chose this solution, or like where did you get it from?
My notes, but how you would get it is okay. Which I actually don't have in my notes, so I'm going to try to reproduce it here, at risk of great personal embarrassment.
We won't know.
Okay. So here's what I do know at the outset. That's equal to some linear function. And that's just because we know that on both halves the derivative is 0. Okay. So now I have to choose a1, b1, a2, b2 to satisfy certain conditions. What conditions do I have up there do I need to satisfy? Boundary conditions. So that'll help us right there. So if I plug in x equals 0, and that would only apply to the first piece. So u of 0 is equal to b1. So b1 has to be 0. So that's out of the picture. And then if I look at u of 1, so that's going to be a2 plus b2. And that has to be equal to 1. So that doesn't eliminate either one of them, but it narrows it down a little bit. And then I need to make sure that that we have continuity. So if I plug in x equal to 1/2 in both pieces, they need to agree. So u of 1/2, I'd plug a 1/2 into both of these. So I'm going to get a1 over 2 for the first piece, and I'm going to get a2 over 2 plus b2 for the second piece. No, wait. Yes, that's right. Yeah, by plugging in x equal to 1/2. So far I have two equations, this one and this one, that relate to remaining coefficients, a1, a2, b2. So what I could do, for instance, is I could eliminate b2. That's 1 minus a2, and I can substitute that in here. So now I have a1, over 2 is equal to a2 over 2 plus 1 minus a2. So I can simplify this a little bit, put a minus there. Okay. So now I just have this relationship between a1 and a1 and a2. Now, okay. Now there is, let's see. As far as the derivatives are concerned, the derivatives of both pieces are going to be 4/3 for the first piece and 2/3 for the second. And there's no way those are going to there's no way that the solution is going to be in C1. There's no way it'll have a continuous, first derivative is continuous on the whole domain of 0 to 1, just because even if we get the functions to match up at x equals 1/2, the derivatives won't. And, well, that would actually require A1 and A2 to be equal. That's what I get for using someone else's notes. Because what I'd like to have is a third condition to nail down A1, A2 once and for all, but I don't have that. Okay. Remember what I said about the risking great personal embarrassment thing? So, okay. And I think what was done here was, okay. And this reminds me of things I've seen elsewhere, but I have a logical explanation. I'm not entirely happy with it, but it's all I got. Because if I fill in what the coefficient is, we have uxx is equal 0 for x less than 1/2. And then 2uxx is 0 for x greater than or equal to 1/2, just by filling in the definition of b. Now, so ux is equal to a1 for x less than 1/2, equal to a2 for x greater than or equal to 1/2, just by taking derivatives. This would not be continuous unless a1 equals a2, but we need, if possible, for what's inside this derivative, so ux here and then 2ux, that's a subscript, ux here and 2ux here, that entity in the outer differentiation to be continuous. So in other words, at the boundary, x equals 1/2, ux should be equal to 2ux on the other side. Just so whatever is inside the parentheses, which is b of x ux, that is continuous. Because if it's not continuous, can't take a derivative. So to ensure b of x ux is continuous, so at least it's in C0, just so that outer differentiation is valid, we require the value of b times a1, value of b from a first piece, is equal to the value of b in a second piece times a2. So a1 is equal to 2a2. So now, if I have this condition and this condition put together, that's two equations for two unknowns. It nails down a1 and a2. So these two together, I won't do the algebra, it gives a1 equal to 4/3, a2 equal to 2/3. And then from there, you get b2 equal to 1/3. All right. Okay. But, so in other words, we got as close to a classical solution as we could hope for. Because at least what's in the parentheses here is continuous. But ux is not continuous. So since a1 is not equal to a2, that means that u is not in C1. We needed it to be in C2, preferably, for a classical solution. So u is a weak solution. Now, here's a funny thing, though. So we have to be careful about evaluating classical versus weak solutions. What's the second derivative? What's uxx on both pieces? And we have ux, so what's uxx? A1 and A2 are constants. Sorry, what?
0?
Yes, it would be 0 for both. Yeah, because, that differentiation, taking first derivative wiped out that. Yeah, and so if we're here, take a derivative of that, and yeah, you get 0. Second derivative is continuous, but we need all the derivatives to be continuous up to 2. So it's not in C2 because the first derivative is so anything in C2 is also in C1, is also in C0, etc. There's a nesting going on. Okay, so any questions about what happened here in spite of my stumbles? Okay. All right. Okay. Definitely took more time on that than I wanted to. But, okay. One more example that I will spend a lot less time on is, I mentioned this PDE before, it's one of the better known ones, Berger's equation. This is a nonlinear, quasi-linear equation. So this equation specifies some sort of initial condition, but so even if the initial data that you choose has infinitely many derivatives, so it's as smooth as possible. What will happen is eventually the solution will fail to be continuous at all. So, and actually, my research has dealt with this equation for some time, like one of my test problems, where I'll start with initial data that's something, a nice function, like sine pi x or something like that. What will happen, I can actually draw the pictures. So you have a solution that behaves like, initially, it's like this. So nice smooth function. And then as t progresses, it starts to propagate to the right, but at different speed. So like this part of the solution at the left is propagating to the right faster than these parts over here. So it's like this, eventually, this part of the solution will overtake this one and catch up to it. And then what we have here is an actual discontinuity. So now with linear PDEs, that never happens. But with nonlinear, it can. This is what is called a shock. When the solution, after some period of time, develops a discontinuity like that one. So there's some sort of jump here. Now, I'm going to explain how this actually mirrors something that happens in real life that you may have actually experienced. Because an equation like this, not Berger's equation specifically, but equations like that can be used to model traffic flow, where the solution U represents the density of cars at any particular spot at any particular time. And the equation for traffic flow can produce shocks, solutions like this that have shocks. So what does this represent in terms of traffic flow? That here there's a growing number of cars, like traffic getting heavier and heavier up to this point, and all of a sudden there's nothing after this. Like they come to a complete stop. It's a parking lot. And after that, nothing. So for instance, like what if maybe traffic was blocked due to an accident, and then past that point there's no cars. Now this sort of thing, and you're probably not likely to experience here in Hattiesburg, because we just have one piddly little interstate, and it's not very interesting. It certainly happens a lot more in California, where you have 10-lane freeways, but you may experience it like down other larger cities like New Orleans or Houston or whatever, where we're driving along and traffic seems to be moving pretty well, but there's a fair amount of traffic, not like too heavy, but all of a sudden it just slows down for no particular reason that you can see. There's no accident, there's no construction, nothing, it just slows. And that is actually a shock. And this actually happened to me when I was, like last year when I was on a road trip, I was going through Houston. And I just seen this from one of the other PDE classes, 606 actually, where what's explained there is the solution develops kind of discontinuity, everything comes, so the cars come to a dead stop, and then, because they've been bunching up, and then they start moving again, all at a uniform speed, like they're in lockstep for a while. And that's actually how the solution behaves too. That we have different speeds of propagation leading to the shock, and then after the shock, propagation continues, but then the whole solution, as like one piece, just moves forward at a uniform speed. And the cars do the same thing. And when I saw it, I was like, wow, that's the coolest thing ever. Math is actually... life is actually following that. So these mathematical models actually get it right from time to time. Okay, so we probably spend that much time on it either, but I think you'd find it interesting. So what you can do is, say if you're going, next time you're driving through a big city and something like this happens, then whoever you're in a car with, you can explain to them what's going on. And then they'll want to throw you out of the car. So. Okay. All right. And I have done that. Like whoever's in the car with was complaining about how traffic was behaving. I said, complaining about the fact that at a stoplight, turns green, and you're several cars back, and you wait forever until you can go. And so we're grumbling about it, and I explained, a hyperbolic system is a finite speed of propagation. And that didn't go over well. Okay. Okay. Fourier methods. Okay. So we're going to look at a few different PDEs that all appear to be related. UT equals UX, XX, XXX, and finally, let's go one more. Okay. Now, this is the advection equation, one-way wave propagation. UT equals UXX. At least for you should know what equation this is. What? Yes, it's a good equation. Okay. This one I have not mentioned before. It's called Aries Equation. This one does not have a name for reasons that'll become clear a little later. Okay. Now, I'm going to find a Fourier Transform, which can be used to greatly simplify the solution of certain PDEs. But there are two types. So there's a continuous Fourier transform, and this is for a case of functions defined on the entire real number line. So problems defined on a infinite domain. Okay. What I've written here in my notes is actually the inverse, but whatever. So a solution is expressed as an integral over the entire real number line, where we have a bunch of wave functions. That's what this e to the I omega x is, times these Fourier coefficients. So this is the actual transform right here. So you think of U as a collection of waves superimposed on each other. So you're adding these waves together to get your solution. These can be complex numbers, and they indicate the amplitude and phase shift of each wave corresponding to the frequency omega. So for solution of PDE on the whole real number line, you have a superposition of infinitely many waves for all the different frequencies from minus infinity to infinity. So rest of frequency, and this incorporates both the amplitude and the phase shift. So like the absolute value of this would be the amplitude, and then the phase shift would be indicated in basically the angular part of a complex number. Okay, so that's the continuous Fourier transform. And the discrete, actually I'm going to define that on a different board. I want to define this. Okay, so that would be 1 over 2 pi minus infinity e to the minus I omega x u of xt dx. So notice we have a minus down here to get the Fourier coefficients, and we don't have it here when we go back to a function of x. So here we're in, this is how you get u in physical space. This is how we get u in frequency space. So we're going from physical to frequency here, from frequency back to physical here. So when people say, continuous Fourier transform, really they mean this to get u in frequency space, and then this is the inverse transform to go back to function of x. Now, the kind I'm actually more interested in is the other kind of Fourier transform, discrete. So discrete Fourier transform, this is for functions that are defined only on a finite interval. Okay. So u is now written as a sum and we still have Fourier wave functions here. We still have Fourier coefficients. But now we have a summation instead of an integral. And then these Fourier coefficients are defined a similar way, again using an integral, except the integral is just on, let's assume the interval minus pi to pi, just for notational convenience. But we could adjust this to any interval. Okay, so really, the Fourier transform itself, there's no difference between the two except what interval you're integrating over. And then the inverse transform, you have an integral for a continuous case, and then an infinite sum for a discrete case. So in other words, k indicates a frequency here, as opposed to omega for the other, has to be an integer. Okay. Now,
and this may be a silly question. Just you have, if that represents the transform, right?
yes.
Okay. Yes. All right.
Yeah. So, yeah, so we can say this is a Fourier transform of u of xt.
Okay.
And then this is the inverse transform of that.
Okay.
Yeah, and then the actual transform gets the minus in the exponential, the inverse transform does not. So you use, this sum, can anyone tell me what this summation is called? Comes up in any introductory PDE class, which most of you have taken. F. It's 2 words. It's like you're playing charades.
Is the name of the summation?
Yes. In this setting of dealing with Fourier transforms and stuff.
Fourier summation?
Close. You're really, really close. you got the first word and the first letter of the second word.
Secret. I'm just guessing out of
Okay.
Series.
Yes.
It's the only other
I know, right?
Yes, Fourier series. Okay. All right. What? All right, so how to solve a PDE like the ones I wrote down earlier. So UT is equal to nth derivative of u with respect to x. So here I wrote for case n equals 1, 2, 3, 4. But we'll just let n be general. Okay. Now, one of the nice things about Fourier series is that it's very easy to express a Fourier series of a derivative in terms of Fourier series of the original function. So if I take this down here and I look at ux, then I'd be differentiating this whole thing with respect to x. Anything else is considered a constant. So if I take the derivative of what's on the inside with respect to x, what am I going to get? So this part right here. Well, it's the only part that would be affected. Take a derivative with respect to x. Yeah. So what's the derivative of that with respect to x? Yeah. So you have ik, and we're only taking one derivative. So ikx. Yeah, so it's exactly the same thing except for respect to k. So if I extrapolate from there, I have, if I take this PDE and write it as everything on one side, set equal to 0. Actually, that should have been a partial derivative, like fancy looking 2's. So if I have this, what I can do is I can take the Fourier transform, that whole equation, so what I get is, you know what? I'm not going to jump directly to that. I want to show you how I get it, even though I'm gobbling up a lot of time. So what I'm going to do with this is I'm going to multiply both sides by e to the minus ikx. Yes.
Where that first, the ut minus partial, where did that come from again?
Oh, I took this.
Oh, okay.
Moved that to the other side.
Okay.
Okay. All right, so you multiply both sides by e to the minus ikx. Okay. And then, I'm deliberately leaving space here. Then I'm going to integrate that from minus pi to pi. And then the order of 2 pi factor up front. I need the space to put the dx. All right, so the reason I'm doing that is basically I'm taking the Fourier transform of du dt and also this nth partial derivative with respect to x. Okay. have from this term, that's the Fourier transform of du dt. But that's just going to be the time derivative of this. So, yeah, really, actually, this integral, if I forget about this now, this integral is exactly the time derivative of this. Because the only thing that depends on t is this. And I'm taking ut. So, what's that time derivative? It's a time derivative of the left side also. So, I get uk hat prime of t. So that comes from here. And what is this? This is a Fourier transform of this partial derivative of u with respect to x. But we already know how that goes. We have factor ik, but to the nth power because we're differentiating n times. Okay. Any questions about how that was obtained? So, derivative with respect to t, you take derivative of a coefficient, which depends on t. Derivative with respect to x, multiply by ik, however many times you need to. Okay. Now I can write it like this. So that's the equation I have to solve. So what I've done is my PDE has now become an ODE, or really a collection of ODEs, because I do this for all integers k. But now I can solve each ODE independently of the others. So in other words, one PDE has been broken down into infinitely many ODEs, like a one-parameter family of ODEs. So now I can go ahead and solve these much more easily than the original. Now, this is kind of like one of the simpler ODEs you'll learn in your first ODE course. If I have an ODE like this, y prime of t is equal to a constant times y of t. And that's the situation we have here. Derivative is equal to the original times a constant, because this doesn't depend on t. Can anyone tell me what the solution of this is? This ODE here. And it's been a while since you had your first ODE class.
Constant.
You add a constant to the end.
Actually multiply by a constant.
Okay, then is it that cosine, sine plus sine thing?
No. I guess it could be written that way if k was complex, but it's not.
It's like e to the kx, or e to the kt?
Yes, e to the kt times whatever y of 0 is. Yeah. Okay. If I rearrange this, and then I integrate both sides, respect to t. And whenever I teach TE, I actually like deriving it this way. But only 2 of you were in that class. Now it's 2 years ago. So the integral of this is natural log of y. And this is kt. And here, yes, you do add on a constant. But then you take the exponential of both sides. And if we use law of exponents, then you're multiplying by that. So that's how a multiplicative constant comes in at the end. Okay. So, questions about that? Now I want to apply the same thing to solve this. So u at k of t is equal to, well, the initial value times what?
How are we going from y prime of t to u hat k of t?
Yeah, so that's what you're solving for this time. So what plays the role of k in here?
IK. N.
Yes, ik to the n. So, so what I have to put here to complete the solution?
IK to N.
That's not all. Look at the solution. But yes, e to the what? Mirror that.
Whatever kt and kt.
Well, what is k?
I, k, and r third.
Yes.
And then a t.
Yes.
Okay.
Okay. That was fun. Okay. So that's the solution for each ODE. So now what we can do is carry out the inverse Fourier transform, this summation. We know what this is now. We can put that back in there. So u of xt is a sum of, so I'll fill in the initial value. Then we have e to the I k x plus I k to the n t. Okay. But now that we have a formula for a solution, we want to be able to understand something about how the solutions behave for different cases, like n equals 1, 2, 3, 4, that I wrote down earlier. So what we have here are functions that describe some sort of wave. And so how is that wave propagating? How is its amplitude changing with time? Like this is the amplitude. This gives the amplitude for the initial condition. But how does that change over time? Because it's going to get multiplied by some factor coming from here. So I'm going to break down certain cases with different values of n. So for n equals 1, what we have is e to the I k x plus t. And the goal is to relate this to e to the I k x, because that's what you have in the initial data. So if initial data at t equals 0 is a collection of waves of a certain frequency, how are those waves changing with time? So how does this function relate to e to the I k x? This came up last time.
To left T.
Yeah, it's a shift of a graph to the left. So all the waves shift to the left. So the whole solution, whatever he started with the initial data, the whole solution is uniformly shifting to the left. Because the solution ends up just being a transformation of the graph of the initial data, because that's the only thing that changed with time. Okay. And because the coefficient of t is 1, it's just plain old x plus t, that tells us the speed. Whereas if I had like x plus 2t, the speed would be 2. But it's the same speed for all frequencies. So that's why the solution is just moving as, it's shifting, it's not doing anything else. So that's n equal 1. Now, if n equal 2, we have e to the I k x, and then I have e to the minus k squared t, because I squared is minus 1. So that means that we have exponential decay. So the amplitude of all the waves, except k equals 0, those amplitudes are decaying to 0 very rapidly. And that's what happens with the heat equation. We have exponential decay in a solution because the solution is smoothing out to a constant, and it does so pretty rapidly. And what about n equal 3? We have e to the I k x minus I k cubed t. Now, I'm going to rewrite this as e to the I k. I want to do it like I did here, where I factor out an I k. And what's left? I have x minus k squared t. Now, this may seem, because of the way I've written it, may seem like a shift, like in the n equals 1 case, but it's really not just a plain old shift of a graph. Why is that?
This would be negative case.
Well, negative would just affect the direction. But well, okay, so it's not the sign, but what is it that matters in this case? Yeah, the fact that there's anything depending on k at all. In other words, the waves are, each individual wave is shifting. But
What
with
does k represent again in this?
Oh, it's a frequency. Well, the k represents frequency. But what did I say about whatever's multiplying the t? What do I call that?
Plus.
Yes, wave speed. Different speeds. Because here the speed is constant. For all k, the speed is 1. Here the speed is k dependent.
So the speed's fluctuating?
Yeah, each wave is propagating with its own speed. And the higher the frequency, faster the speed. They're all going to the right because of a minus. So when we have that situation, so here, a uniform shift, that's advection. Here, when they're decaying, that's diffusion. Here, where the waves are propagating but with different speeds, that is called, and I think the term will make sense when you think about it, dispersion. That we have, that whatever content you have in initial data is scattering. questions about that one? And finally, n equals 4. So we have e to the I kx, and then I to the 4th is plus 1. So it's e to the positive k to the 4t. So what's happening to the waves in that case?
It's not decay, but it's growth.
Yes, exponential growth. And this comes to a reason why. So in other words, whatever initial data is, the solution is going to explode exponentially over time. For larger values of k, those high-frequency waves will blow up more because of the factor of k to the 4th here. So when we have a problem where we may have a solution, but the solution exhibits this kind of exponential growth over time, what kind of problem is that? Using a term that came up on the first day. Okay. I don't mean about physical effects, but just
Ill-posed.
yes, this is an ill-posed problem. That's why I didn't have a name for PDE, because it doesn't reflect anything that happens in reality. Imagine if it did. Actually, that reminds me of an ODE that I once saw in a calculus book. That's actually similar to this one, except there's a slight change. Y prime is equal to a constant times y to the 1.1. So it was actually used to model reproduction of rabbits. And in the problem, you're supposed to show that you go ahead and solve it, and you find out that at a certain time, a certain finite amount of time, the solution, y, which represents rabbit population, literally becomes infinite. So the solution has a vertical asymptote at a certain time. So soon you have infinitely many rabbits. So the equation was actually called the doomsday equation. What a way to go. So sometimes mathematical models can be just a little bit off. But actually, one of my professors at Stanford wrote a paper about modeling the movement of earthworms. So he had some sort of PDE that modeled their movement, and from analyzing his PDE, the model seemed to suggest that earthworms could move like 200 times faster than they normally do. So I don't know if that meant that under the right conditions that an earthworm could really haul ass, or maybe his model was a bit off. But okay. So we can tell a lot about just how these PDEs behave by looking at Fourier series. Now, Fourier series are particularly useful for PDEs that have constant coefficients, as these do. And my whole research is about changing that to variable coefficients, but whatever on that. So most of you deal with that enough outside of class. But we can actually I don't even necessarily go as far as solving the PDE to get an idea as to the behavior of it from a Fourier series standpoint. So if we assume the solution has a certain form, so we assume that the solution has this form, u of xt is equal to e to the I kx times e to the minus I w t, where w is unknown. Now, I'm going to mention a term here, because normally what I would say is, okay, I'm making this assumption that the solution has this form. Now, what particularly snobby mathematicians say, and this is how you can pick them out of a crowd, is that making an assumption like this is called an ansatz. Like we make the ansatz that u of xt is equal to this. Why mathematicians still talk like that, I don't understand. I've never felt the need to use that term myself, but at least I can if I really need to. Like, I guess if I want to blend in or something at a math conference. So, but yeah, I mean, in case you come across this word because it's in the notes, then you know what it means. So, all right.
What is that like? What origin is that word? Is that German?
I haven't looked it up, but probably, yeah. So. Okay. So, well, when you're teaching, I don't know if it would fit in college algebra, but you can make your students go like, what did she just say? Okay. Okay. So what you can do is substitute this into the PDE, and then you solve for W. And I get it right this way. W equals W of K, indicating that most of the time W is going to depend on K. So what does W mean? You can actually get that from how I've written this. Because I can rewrite it this way: e to the I k x minus W over K times T. So W over K is the wave speed. Because for each K, the solution is a shift of a graph of e to the I kx, and this indicates what the shift is as t increases. So for example, if W is just a multiple of K, then the wave speed, W over K, would be a constant. So we have advection. Okay. But in a case where this quantity is complex, then it's best not to write it this way, like leave it like this, because then what we have is a different phenomenon. We have exponential growth or decay of each wave. So it just depends on what you get for W. So I'm going to do an example of how you would. Okay. So what do you get for W as a name? It's called the dispersion relation. So different forms of W give an idea as to how your solution behaves. Is there advection? Is there diffusion? Is there dispersion? And so on. Okay. So I'll do some examples. Like the a wave equation. UT UTT is equal to c squared uxx. So all I have to do is take this, use my ansatz, and substitute that into both sides of the PDE. Now, the nice thing about having exponentials is anytime you take any derivative of an exponential, you're going to get the same exponential times something. So I'm not going to bother writing down the exponential because I know it's going to show up there in every term. So what I really care about is when I take the derivative of that with respect to t or x or whatever. So for example, if I take the derivative of this with respect to t twice, then I'm going to get minus iw squared for the left side.
What? Where'd you get that from? Sorry.
Take a derivative of this with respect to t. So,
Okay.
yeah, first time I get minus I omega, then I do it again. What about, that's for the left side. What about the right side? I'm going to have a c squared still. That's going to be there. What else will I get? Second derivative with respect to x.
IK squared?
Yes. Because every time you differentiate that with respect to x, multiplied by factor of ik. All right. So now let's simplify this. So, well, minus I squared is also minus 1. So I get minus w squared is equal to, that'll also give me a minus. So minus c squared k squared. So I can cancel out the minuses. And then I want w. So I'll take the square root of both sides. So w is equal to plus or minus ck. All right. So that is the dispersion relation for the wave equation. Remember when I said if w turns out to be a multiple of k, like a constant multiple of k, then because of this, waves have constant speed. So that's what happens here. This is advection. But because of a plus or minus, you can have propagation in both directions. Because positive w, or w over k, is moving to the right, negative moving to the left. Okay. So, once you have W, the growth factor in each wave is e to the minus IWT for whatever your W is. So you just take that and just plug that back in here. Now, actually, it's the absolute value of this, because growth factor ought to be a real number. So, if we look at the growth, we get absolute value of e to the minus, e to the plus or minus ICK. Ick. So, when you have a complex number like this, e to the I something, does anyone know what its magnitude is? You may not have had enough dealings with complex numbers to know, but no. If the I wasn't there, then it could get as large as you want of k. But it's at I that changes everything. Well, that's the same as cosine ck plus or minus I sine ck. In other words, it is a point on the unit circle in the complex plane. That's a terribly drawn circle, I know. Where the real part is the x-coordinate, the cosine, and then the imaginary part is the y-coordinate, the sine. And the magnitude of the point on the circle is the unit circle.
1.
Yes. The growth factor is 1. In other words, the waves do not grow or decay at all. Because we have advections, this propagating is neither gaining or losing mass as it propagates. So that's what happens whenever you have this kind of dispersion relation, where so it's sort of like a conservation of mass thing going on. That the amplitude of a wave stays the same for all time. Okay. By contrast, heat equation ut is equal to, see if I have a coefficient, duxx. Okay. So here I'm taking derivative only once with respect to t. So on the left side it's going to have minus iw, and then on the right side it's going to be very similar to this. It's going to be minus d k squared. So the minuses go away. Okay.
And then k squared. We're still going back to that top.
Yeah, we're still using this.
Yes. And so the k squared, because we're taking it with respect to
X
twice.
twice. Yeah. So the right side worked out almost exactly the same, just a different coefficient.
But there's no I. I think that's why I'm confused.
Oh. I went down to this step.
Oh.
Yeah, so I simplified it. I squared it along the way. Sorry.
So we didn't go back up to the. Yes.
Okay. But that's equal to minus dk squared.
It's like the rule for imaginary numbers.
Yeah, I squared is minus 1.
Yeah.
Okay.
Sorry.
Okay. All right, so W turns out to be complex this time, whereas it was real the previous time. So then we look at the growth factor. We have e to the minus iw t. So now we have minus I and minus I. Well, minus I squared is minus 1. So we have e to the minus dk squared t, which goes to 0 as t increases. So, but that's what we expect of a heat equation. All the waves are decaying exponentially as we go. Okay. Any questions about that one? All right. We're running low on time. That's going to make Wednesday interesting. Although, how much do I have to cover on Wednesday? Actually, it's not so bad. I just have to be careful not to digress too much. So, you need to remind me of that. So I'll do one more. This is a PDE that I don't think I've brought up previously, but it actually is featured in one of my papers. So this is the Schrodinger equation. I don't believe there's anything to do with Schrodinger's cat. But Schrodinger did a lot of things. So this PDE has an imaginary coefficient, I, ut, is equal to uxx. So very similar to the heat equation. In fact, we're just going to have an I, extra I on the left side, and there's no coefficient d on the right side. So if I differentiate, so if I substitute that u into the PDE, I'm going to get I, and then minus IW. And then on the right side, it's going to have minus, no, it's plus. Oh, I'm sorry. Over here, there should not be a minus. Doesn't affect the result. Like that. Yeah, because the minus is only for the t side. Like right here. Okay. So, whoops. IK squared. Okay, so now I can go ahead and simplify this. So I times minus I is equal to 1. I just have w on the left side by itself. And then I have minus k squared on the right side. So this time the dispersion relation is real again, like it was for the wave equation, but still something different. Not a multiple of k, but rather we have k squared, so that's going to affect things. So the growth factor is e to the minus I w, which is minus k squared t. So I'll clean that up. So it's e to the I k squared t. Well, this is 1 again, similar to the other case. So there's no growth or decay. But the wave speed, like if I divide this by k, the wave speed depends on k. So when the waves are traveling with different speeds, what physical effect is that? Dispersion, yes. So that we can see from here. So anytime so if a wave speed is not a multiple of k to the first power.
Wait, can you say it one more time?
If a wave, if the dispersion relation is not a multiple of k. So in other words, w over k is not a constant.
So
when w is not a multiple of k, that's when the wave speed depends on k. So that's chances are when we had dispersion, like we have in this case. Okay. All right. So now we have some idea for certain PDEs the different behaviors the solutions can have, whether it's the waves propagating or diffusing or dispersion, and how we can spot them mathematically. Because now you get an idea, you can see from the form of a PDE. Because what I was doing here, I was not trying to solve a PDE at all. I was assuming a solution has a certain form and substituting it in. But that's all I was doing. And even then, we're able to have some understanding of how the solution behaves. We can also see, like from one of the examples earlier, like n equal 4 case, that a certain problem can be ill-posed. based on what the Fourier coefficients would look like over time. Okay, so, but yeah, so it's not like lower level math classes where you're just solving this equation. You're not able to interpret what we're getting to. Okay, so looks like I'll have Laplace's equation for Wednesday, but the first homework problem deals with Fourier series and dispersion relations and things like that. So take a crack at that, and I mean, homework 1 is not due for like forever, so because there's other problems too that are more MATLAB-y. So try to get through Laplace's equation stuff on Wednesday. If you can, see if you can look at homework 1. I should mention on the site where I post the homeworks, there are also there's a file with hints that came up from the last time I taught this.
What?
There's a separate file that has hints on all the problems.
Yeah.
All right, so if you get a chance to look at it, we have time for questions on Wednesday, or it can wait till Monday. So whatever you want to do. Okay.